Just give me a minute and then we'll start the session.
Hello, ma'am. Am I audible for you? Can you hear me? I have one doubt.
Yeah,
Today you will cover whole week six summary
yes,
from scratch.
yes.
Ma'am, I haven't seen those website videos. So is that okay for me? I need
It
to
should
watch
be
them.
okay. If you want to, you can. Otherwise, we'll be covering almost everything here from week 6.
Okay. In detail or like just in summary wise?
We'll cover everything that you need to know. Like we might not do proof of everything because that's not required, but we'll do everything that you should know for your exams.
Okay. Ma'am, is that any possible to score 90 above? Because I need to maintain my CGPA, I need to score in quiz to 90. So if I watch every TA and every instructor session, then I will achieve.
You don't have to watch. See, if you feel like you can go through the videos that are there on your portal, right? Those should be enough, and you should be able to do questions. The instructor sessions and TA sessions are basically for summarizing stuff and for you to clear your doubts here. So if you already are through the week or you're good with that week, you don't need to attend you don't need to see them. But if you have doubts, you can come to the class and ask them. You don't need to attend all of those. If you're already good with the syllabus for that week, you don't need to, right?
Okay, got it, ma'am. Thank you, ma'am.
Okay. So these summary sessions are to summarize everything that you've done in that week. Okay. So we'll start with the definition of what a logarithmic function is. So logarithmic function is basically fx, and you're defining the function as log, and we have something called a base. Let's call the base. Let's just have the base as a. We'll see what a base is, and then x. So this is your variable here, which is called the argument of your function. So your x here is that the quantity that varies here is this one, this x, and your a is supposed to be fixed. And what does this function mean? This is basically the same thing as if I say I have a to the power y is equals to x. If this is the case, that I can write this thing as log base ax is equals to y. This means that if I raise this thing to this power, that means if I raise a to the power y, I should get this x. For example, let's say if you have log base 2 and here you have 8, then you should have a 3 here, because 2 raised to the power 3 should be 8, right? So by that's how your log function works. Okay. Then there are some conditions for you to define the log function. Let me just write those conditions here. The first is your a, the base. This is called the base for log function. So your base should be greater than 0, and you can't take the base to be 1. So these are two conditions on your base. Why it should be why it cannot be 1 is because if you take a to be 1 here, then you cannot have 1 to the power anything is always 1. That's why there's no point of having that here, right? And the second condition is on your x, which is x should be greater than 0. So the second condition is on your domain of this function. If log base ax is a function, then the condition is on x. That means this would decide the domain of the function, right? Condition on the argument, x defines your function's domain. So x should be greater than 0. You can see here why x should be greater than 0, because any number, no matter negative number, positive number, even if you, and we're not taking the negative numbers here, right? Your a, because we're taking a to be positive, that's why any positive number raised to any power If I have a greater than 0, then a to the power anything t should be greater than 0, right? It cannot even be 0. A to the power t is not even 0. Because if you've seen the graph, if you've seen the graph of a to the power x, it's either this, depending on a, right? Or this. That means your y is never 0. So it's never 0 because it never crosses, it never comes here. Your this graph never touches your x-axis. That's why your y for this curve is never 0 and it never goes down this line. It never comes here. That's why your y is basically the height, right? This function, your x is this distance, and y is this height. So your height's never negative here in either of these functions. That's why this function a to the power x remains greater than 0. And because a to the power x remains greater than 0, that means this thing. What we're trying to say here is because this quantity is always greater than 0, that means x is always greater than 0, which means if you have x here, you need to have a number greater than 0, right? So these are the
Ma'am,
conditions.
ma'am, ma'am,
Yeah.
I don't understand graph. Can you repeat again? And ma'am, please, like teach slowly. Actually,
Okay.
lots of people and me is not getting.
Okay.
You
What
can
we're
hold
doing
the,
here is
yes, yes, ma'am.
Under each from
we're saying
starting.
this is the starting. What we're doing here is we've defined the function. You already know the function a to the power x, right?
Yes, ma'am. Yes, ma'am.
We
Yes,
know what
ma'am.
this function is. When you take this function, and if I say a is greater than 0, this quantity is always greater than 0 then, right? If I have 2, let's say, and if I'll do minus half here, then what is 2 to the power minus half? We don't
Uh,
care what it
two.
is, but it's greater than 0, right?
Yes,
So
ma'am.
if I have a greater than 0, a to the power x is greater than 0, no matter what x is. It's always greater than 0, right?
Yeah, yeah.
So
Ma'am,
that's what
2
we're doing
upon
here.
2 to the power minus 1 by 2 is equal to 2 upon 1, 1 by 2 upon 2, 1 upon 2 over, na?
It's
It's,
this. 2 to the power minus half is this. 1 by root
yes,
2.
1 upon 1. Yeah, ma'am.
So, and this number is positive, right? So all we need to know is if you will take a greater than 0, then this quantity a to the power x is also greater than 0 for every x, right? Now, if this is always greater than 0, I said if I have a to the power x is equals to y, the other way of writing this is log ay is equals to x. This expression means that if I raise a to the power x, I'll get y, which is the same as this, right? So these two expressions are equivalent in that sense. Is this clear? Now, if I want to have the y, what's the domain of this function? If I want to know this, what should be the condition on x? That's the domain, right? Then what should I take? Can I take a negative number here? Can I take
Yeah.
something negative here?
X, yeah,
Okay.
you can take, ma'am.
If I'll take something negative here, let's say I've taken log a minus 2, and what will this be? Let's say this is y. Okay, this, let's say this quantity is y. Now, if this quantity is y, that would mean that a to the power y should be minus 2, right?
Ma'am, I don't
Is this
understand. I
okay?
didn't get it. No, ma'am.
These
Please repeat
two
again.
things are these two things are equivalent, right? If I when I say log, okay, forget this. Let me just write
Is
exactly like this. If I
is
have this thing,
is my network damaged or
x,
Ma'am, your voice is cracking.
yeah,
okay.
yeah.
Is it better now?
Uh, Actually, it was cracking since the start of the session,
Yeah.
and so
That's why, ma'am, like, and sometime your speed is going to be 2x and sometime your speed is going to be 0.5x.
Okay.
Yeah.
So just 1 second.
yeah. If if it's okay, please try to reset the internet because even your mouse is also like
Okay.
moving
Yeah,
very
just
slowly.
1 second. Just give me a minute.
Yeah, sure.
Is it fine now?
Yes, yes.
Okay. So we were doing this thing and we said that these two things are same. Whether I say a to the power y is equals to x, or I say log base a, x is equals to y. This expression basically means when I raise this base to the power y, I should get x. These two things are same. All right. Now, if I want to find what x can I take here, you said I can take minus 2 here because someone said that I can take negative values here, right? Let's say this quantity is, we'll have some value here, right? Let's take a to be, let's also fix a. Let's take 3 here. Now, if I can have negative value here, that would mean that I'll have some number here, right? I don't know what that number is, but let's just assume that number to be y. We don't know what this value is, but let's say it is y. If it is true, then this should be the same as 3 to the power y is equals to minus 2, right? Because these two statements are equivalent. That means another way of writing the same thing is this, right? Is this clear?
Yes, ma'am.
Okay. So can I have a number? If I'll raise 3, I don't know this number. I can't find these numbers, but I know one thing, that 3 raised to whatever power will always be greater than 0, right? We discussed this thing here. If a is greater than 0, this implies a to the power x is always greater than 0 for all x belonging to real numbers. So no matter what
Ma'am,
power I take here, yeah.
ma'am, a could be negative now. Maybe a
No,
could be negative.
we already said here that A is positive. We have this
Uh,
condition here.
okay, it's a fixed condition.
Yeah. So that means here you cannot have anything negative, right? That's why the other condition that comes along it is that your x should be greater than 0. That's why we've taken this condition that your x should be greater than 0. So far, what we've done is we've defined the function in this manner. Log base ax. This is the function that we've defined, and we've said that this function is equivalent to saying, now if I say, if this is my function, y is equals to log base a x, that this means that a to the power y is x. So let's say if I have, we've taken an example too. Let's say I have log base 2 x function. All right. This is the argument of this function. Argument is this thing. The x that you put here is called your argument, right? So if this is the argument and my result is, let's say, that means for different values of x, I'll get different values of y.
Yeah.
What? So if I'll take different values of x, I'll get different values of y, right? So this will be, for example, let's say if I take x value to be 2, then y's value will be 1, right? If I'll take it to be 4, I'll get 2. I'm taking natural numbers here so that I get something nice here, right? If I'll take 8 here, I'll get 3 here. Now, if I'll take log base 2 and then if I'll take 5 here, then I'll get something here, which will be, if I have to write it, it will basically be 2 to the power
Excuse me,
1
ma'am.
by 5. Yes. Sorry. Yeah.
Ma'am, how 3 comes?
3 because 2 to the power 3 is 8.
Okay, ma'am.
Okay. So this is how your log function works. Now, I know that this definitely is not a natural number, but there is some number which when raised to power 2 will give you 5. And this is that number. So what you're doing here is, what is this function, this number? This is a number, right? And what kind of number is this? This is basically a number which when raised to power 2 gives you 5, right? If I'll raise this number to the power 2, I'll get 5. This is that kind of number. So the number which when I'll raise to power 2 will give me 5. I am representing that number with this symbol, log base 2 5. Is this okay? This is just the basic definition of your
Okay,
log
ma'am.
function. That's it. We've just defined the log function. Okay. Then let's come to the domain. And what's the domain of this function? Your function is, let me write it again. This is log base a, where a is a fixed number and x is your variable and y is your output. So your input is x, your output is y. What's your domain? We've already seen this. This is what we discussed just now, right? That I cannot take if a is great, if I'm taking a to be greater than 0, then I cannot take, this is a fixed condition on x, then my x has to be greater than 0, right? We just discussed it. Because a to the power y cannot be a negative number, or it cannot be 0 either, right? That means because a to the power y belongs to 0 to infinity, that is why my x, that means the domain of this function should be from 0 to infinity, right? So my domain is this for this function. Is this okay?
Yes, ma'am.
Okay. Then coming to the range part, what is the range of this? This function is
All real numbers.
all real numbers, because the range of this would be, if you have a to the power y is equals to x and you're writing this equivalently as log ax. So your range is basically all the possible values of y here, right? All the possible outputs that you get is the range, and those outputs are coming from here only. So you can consider the y from here. So the domain of this, simply the domain of this becomes the range of this, and the range of this becomes the domain of this, right? Is this part clear?
Can you repeat again with the example? Can you take
These
an
two
example?
functions are, do you remember what invertible inverse functions are? F and F
Yeah.
inverse. Let's do it that way. If you have a to the power x is equals to y, if this is a function, then what's this function? Log base ax. This function is the inverse of this function. If this is f, then this is f inverse. And you must have done this thing in the previous week, that the domain of f inverse is the same as range of this, and the range of this, and the range of this is the same as domain of this, right? So domain
Yes,
of
ma'am.
f is the range of f inverse, and range of f is the same as domain of f inverse. So that's what we're doing here. Now we're saying, that means what is the domain of this function a to the power x? If I look at this, then x is the domain, right? And y, what you're getting as output is the range. Now if I'll take the opposite of it, this will become log a y is, forget that too. What's the domain of a to the power x function? What's the domain of this?
0 to infinity.
0 to infinity. That means this is the range of log base ax. Is this clear? If you want to see how these two are inverses of each other, this is how it is. Log base a and a to the power x. What are the inverse functions? They are, if I operate f with f inverse, I should get identity, right? Those are called inverse of each other. So I have log base a, and then I've composed it with a to the power x. What will I get here? What should be the power of a such that I get a to the power x? This is that value, right? Let me say this thing is y. Then what power should I raise a? This means a to the power y should be a to the power x, right? That means your y should be equal to x. So you'll have x here. Similarly, if I'll do a to the power log base ax, this is equal to, let's say this is y. This one's also x. That's why they are inverses of each other. This one also comes out to be x. So because a composed with ax composed with log base ax, and the opposite one, log base ax composed with ax gives you x. That's why they're inverses of each other. And for the inverse functions, you can simply apply this range thing, right? Range of this is the same as domain of this, and range of a to the power x, which is real numbers, is the same as domain of Wait, the domain of this is R. Domain of a to the power x is R, right? Is this fine?
Oh, ma'am, you said x cannot be negative, so how it is r?
Yeah. This is what is the domain of a to the power x function, and why can x not be negative here?
0 to infinity.
The domain of a function is the input that you can have here, right? Why can't I take negative numbers here? Can I not raise a to some negative number? Can I not take a to the power -2 here?
Yes, ma'am, we
It's
can.
a valid thing, right? Why is -2 not in the domain? Then you're saying 0 to infinity. Negative numbers are also there. All numbers are there. The domain, we
Okay.
have discussed this last week. At least go through last week's stuff. Domain of a to the power x is real numbers. That's why the range of log function is real numbers. And range of a to the power x is 0 to infinity. If you remember the graph for a to the power x, it was this or this. Either way, your range is 0 to infinity, 0 not included. This 0, x is equals to y is equals to 0 line is not included in your domain, in your range. This is not included in your range. So that is why your range of a to the power x is the same as domain of this thing, which is 0 to infinity. Are we clear till this point? This is the takeaway. Domain is 0 to infinity and range is real numbers. Let's do one example if things are not very clear. Let's say you have log base 5, p is equals to 2, and then log base 2, q is also equals to 2. And then let's say you have to find the value of p to the power 4, q to the power 4 by 100, let's say. You have to find this value. Then what does this give us? You have to find this. We already have log base 5, p is equals to 2. This implies 2 to the power 5 is equals to p. This implies 2 to the power 2 is equals to q. Now I have the value of p, I have the value of q. I have to find the value of this expression, right? So this is 2 to the power 5 whole to the power 4. This is 2 to the power 2 whole to the power 4. And this is divided by 100. So this will be 2 to the power 20. This will be 2 to the power 8 by 100. And you can add these powers then, right? So this will be 2 to the power 28 by 100. Is this okay? Okay. Then coming to the next thing, we have the graph of before graph. Let's just do this thing. So if you remember a to the power x thing, the function, this function when we discussed, we took two cases, right? One was the case when we took a. Am I audible?
Yes, ma'am.
Yeah. Am I audible to you people?
Yes, ma'am.
Yes, ma'am.
Okay. So when we did this one, we took two cases where one was a greater than 1 and the other was a between 0 and 1, right? We took these two cases. Similarly, we'll do the things here for this function too, log base ax. We'll have to, because let's have this function and then we have two cases when a is between 0 and 1 and the other is when a is greater than 1. So if your a is between 0 and 1, your function looks like this. And if you remember, we have discussed this part too, right? How does your a to the power x function look like? Let's do this in rough part. Your a to the power x for a between 0 and 1, what does it look like? Let's say this is your function fx. Then the inverse, we have already seen this, that the inverse of this function is log a x, right? Where a is between 0 and 1. So if this is your function, then the inverse of this function is this. Are we clear till this part? Am I audible?
Yes, ma'am.
Okay, then just okay. So if these are two functions, this function is inverse of this function. Then how do we sketch the graphs of f and f inverse? We discussed this in last class, that if your y, this is your y is equals to x line. If you have f here, then if this is your fx, then the inverse of this is here, the mirror image of this, right? Along this axis. So we'll do the same thing here. If this is your y is equals to x line, and we have our function is a to the power x. A to the power x for a between 0 and 1 looks like this, right? It's a decreasing function. We did this in last class, that the graph for this function looks like this. And we know that the inverse of this function, which is this function, the graph of this should be the reflection of this. If this is fx, then f inverse should be this, right? This should be f inverse of x, because this is the mirror image of this one along this mirror, right? This is y is equals to x. So the graph of this one looks like this.
When can you show the graph along?
This one. Similarly, if you have f a to the power x for a greater than 1, the inverse of this is log base ax, a between, in fact, it's the same a. Let's say I've taken some a, and here I'll take b instead. B to the power x, where b is a fixed number and that b is greater than 1. Here, this b is a fixed number, and this b is greater than 1. Then the graph of b to the power x looks like this, right? It's an increasing function, looks like this. This is f. And if this is your y is equals to x line, it looks like this. Then the image of this will be this. Not the image, the reflection of this. The reflection of f about this y is equals to x line. This is y is equals to x line. This is the reflection f inverse. So that means when your a is between 0 to 1, for that log base ax function looks like this. When your a is greater than 1, in that case, your log base ax function looks like this. So it should be this then. Is this okay?
Yes, ma'am.
Okay. Then we have x-intercept. What's the x-intercept of this? How do you find the x-intercept? You put y equals to 0. So your function is y is equals to log base a x. So you put y is equals to 0. Even though you can see from here that we have an x-intercept, right? This is your x-intercept. So for you to find x-intercept, put y is equals to 0. You'll have log base a x is equals to 0. What should be x then?
1.
1, because this is the same as a to the power 0 is equals to x. That means your x should be equal to 1. That means your x-intercept is, that point is 1, 0. So this point is 1, 0. Now coming to this one, the x-intercept of this is, again, you do the same thing here. So you'll get, because A, how do these two differ? They only differ in A, right? Here your A is between 0 and 1, and here your A is greater than 1. So the only difference is in A. And does A affect how we've solved this? Does my x-intercept depend on A?
No.
No, ma'am.
It doesn't, so the x-intercept should remain the same here, right? So that means the x-intercept is the same, x is equals to 1 and y is equals to 0. This is your x-intercept. Okay. Then the y-intercept, the graph tells us very clearly that we don't have a y-intercept here. This keeps coming closer to your y-axis, and this one keeps coming closer to your y-axis from here on the negative side, but it never touches your y-axis. That means you don't have a y-intercept. But let's see. For this, you do x equals to 0. So in this one, log base ax, you put x equals to 0. And then you find the value of y. But I can't put x equals to 0 because for this function, the domain is x greater than 0, right? That means I don't have a y-intercept at all. No y-intercept. And here you'll have the same thing, no y-intercept. And then let's see, I know my domain is 0 to infinity in both cases. Let's see what happens when x tends to infinity. What happens when x tends to infinity? Here. Where's your y going when your x is going to infinity? When x increases on this side, where's
Minus
the height
infinity.
going? Going to minus
Minus
infinity.
infinity.
So that means this is, when x tends to infinity, y goes to minus infinity. Or you can say your y is log base ax, so this goes to minus infinity. Similarly, when x tends to infinity here, what's happening? X is tending to infinity, y is also going to infinity, right?
Yes.
So that means this will be log base ax, this goes to infinity. Now let's come to when x tends to 0. The other end is 0, right? In your domain, the other end is 0. You can't go to minus infinity, but you can go to 0, right? So when x tends to 0, this is when x tends to 0. This is your y-axis is x is equals to 0 line. You know that, right? This is x equals to 0 line. And this is y is equals to 0 line. So when your x comes close to this line, x is equals to 0 line, where does your y go? Where's the height of this graph going?
Plus infinity.
Plus infinity. So this is when x goes to 0, your log base ax goes to plus infinity. And this one, when x tends to 0, here, when x is coming closer,
Minus infinity.
minus infinity, right? Log ax tends to minus infinity. And then about the increasing, decreasing behavior, we're only left with that, right? So you can tell that from here. If this is your curve, then this is a decreasing function clearly, and this one is an increasing function. In fact, you can also call them strictly increasing. This is strictly increasing, decreasing. This one was decreasing, right? Yeah, strictly decreasing. And this one is strictly increasing. One very important thing to note here, you can note it from the graph too, that this function is a 1-1 function. If you will perform the horizontal line test here, you will see each horizontal line cuts the curve at only one point. At most 1 point, right? So this is, both of them are 1-1 functions. This is also 1-1. And we did discuss there the natural exponent, right? E to the power x. So if I have fx is equals to e to the power x, then the inverse of this should be, what should be the inverse?
Log
It should
base
be
e to the power x.
log base e
x.
and x is the argument. This we write as natural log of x. So this is just a notation. Instead of writing this entire thing, we represent it by ln x.
ऊपर
And this one, by the way, is in this category. This one, where a is greater than 1. So its graph looks like this. Okay. Then we have properties of logarithm. So the same way we discuss the properties of a to the power x, we have properties of log of x, log ax, and they are valid for all x, for all a not equals to 1 and greater than 0.
निकाल दो चार्जर पावर बैंक लगा लो अभी जरूरत नहीं है चार्जर की निकाल दो
Okay. So first property is this. Log base a xy is the same as log a x plus log ay. Then the second one is log base a x by y. This is the same as log base ax minus log base ay. Then we have this log base a x to the power n. We have proofs of these properties, but okay, we'll do the proofs towards the end. If we're still left with some time, we'll do the proofs of these properties too. So this is n log base ax. And this a special case, a case of this is log base a, and if you have 1 by x instead, so I can write this as log base a x to the power minus 1, and we know that the power here comes out, so this will become log base ax and a negative sign here. Then the next one is this one. So let's say if you have different base and you want to convert this base to e base, a natural base, then it will be log b by log base e a. In fact, you can convert it to any base, I guess. You can, if instead of e you want to convert it to some other base, let's say you want to convert it to c as well, you can convert it to that too. Some different base from these two, different from a and b. Fifth is if you have log of this, then this can be written as 1 by log. So if you want to interchange the argument here with the base, you can change it by reciprocating this thing. And these are the basic ones where you have log a is equals to 1 because a to the power 1 is a. Then log a, and if you have 1 here, then this should be 0, no matter what your a is, because a to the power 0 is 1. Then log ax is equals to x. We've already seen this when we were discussing that these two functions are inverses of each other. We have seen by this is x, right? And then the other one is a to the power log ax, this is equals to x. Let's say you can see this as if you consider this thing as log ax is equals to y, you'll have a to the power y is equals to x. And if you change this, you will have log base ax is equals to y. Okay, so we're getting the same thing. This is how you define log ax, right? The function, this is defined as what should be raised to the power a, which gives you x, right? If you're saying that your a, this is the same as what should be raised to the power a, that gives you x. If you have x here, then what should be the power here? And the power should be this, because let's say you have this function y is equals to log base ax. This is the same as saying a to the power y is x, right? And your y is the same as a, put the value of y from here, you will have a log a x, this should be equal to x. So this is the proof of this. We've done the proof of this thing, that if your y is, if you consider log base a x to be y, if you consider this exponent as y, then a to the power y, by the definition of log function, a to the power y should be equal to x, and your y is the same as log base ax. So we have done this is the proof of this one. We've done one proof. The proof of this, and this, that they're too easy. And we'll come to the proofs of these ones later. So these are the properties. Overall, we have 5 properties in total. So these basically are more or less all the properties that you need to use. And then one property that I've not mentioned is that I'll mention that too. That is, if you have log a to the power, let's say in the base you have log a square x, then this is the same as log a x to the power half. These two things are same. So let's say if you want to change the base from a squared to a, then you should take power half here. So similarly, let's say if you have log a to the power n x, and you want to change the base to a, instead of taking taking the base to be a to the power n, if you want to change the base to a, then this should be x to the power 1 by n here. This is it. These are the properties that we have to solve questions. Now we already know, let's do some questions only. Let's do one example on how to find the domain of the composition of log functions with some other function. Let's say we know that log ax, the domain of this is 0 to infinity, right? Now let's say instead if I have log base 3 x plus 1. Now this is my argument. That means my argument, instead of x, I have mod x plus 1. What should be the domain of this? How do we find the domain of this one? So we already know whatever's in the log, that thing should be positive, right? If I have log base 3 t, then t should be greater than 0. Now, if I have, instead of t, if I have log base 3 mod of x plus 1, then mod of x plus 1 should be greater than 0, right? So that means, and mod of x plus 1 anyway is greater than 0, right?
Yes, ma'am.
No matter what value of x you take, mod x plus 1 is always greater than 0. That means every x is a valid input here. The problem is, let's say you have something like log of x plus 1. Instead, if I have log base 3x plus 1, now my problem is I don't want a negative number or 0 here. But if I'll take x is equals to minus 1, I'll have log base 3, 0, which is not valid, right? This is a problem. I can't have 0 as argument of log. So to avoid this problem, we have to do x plus 1 greater than 0, right? So we have to find all the x for the domain of this function. We have to find all the x such that x plus 1 is greater than 0 for the domain of this function. But if you have log of mod of x plus 1, you just need to make sure that whatever's inside your argument of log, that should be greater than 0, and mod is always greater than 0. So no matter what value of x you take, it's always greater than 0. So the domain here will be R. Is this fine? Or if you wanted to do, you want to do this the way we did
But
in
if,
the previous
ma'am,
week.
hello,
Yeah.
ma'am.
If x
Yeah.
equal to
But
minus
if-
1, then
Yeah, that's
Yes,
left,
I
right?
have seen out.
Yeah, that's left. So you can't take minus 1 here because this mod of x plus 1 should be strictly greater than 0, right? Should not be equal. So that means your mod of x plus 1 should be greater than 0, or mod of x plus 1 should be strictly less than 0. So this will give you x greater than minus 1 or x strictly less than minus 1, which excludes x is equals to 1, right? That means x should not be equal to minus 1. Yeah. So this would exclude minus 1. This is it. Or if you want to go by the proper definition of this, we have discussed the definition of domain of log of FOG, right? Sorry, domain of FOG. So domain of FOG was, if you remember from last week, it was domain of G intersected with X belonging to real numbers such that G of X is in the domain of F, right? If you want to use that definition, that's also fine. So if you have log base 3 mod X plus 1, then what is your G? Your G of X is mod of X plus 1. Your F of X is log base 3x, right? And if I'll apply this definition here, the domain of G is real numbers and this set X belonging to R such that Gx belongs to domain of F. What's the domain of F? Domain of F is 0 to infinity.
0 to infinity.
And Gx is mod X plus 1. So for you to want, this means mod of X plus 1 should belong to 0 to infinity. This is the same as saying X plus 1 mod should be greater than 0 and less than infinity, which is true, but there's only one problem, that this should not be equal to 0, right? This would mean that your X plus 1 should not be equal to 0, which means your X should not be equals to minus 1. So this is the only condition on your domain, that your X should not be equal to minus 1. That's it. That's why we need to remove minus 1 from our domain. R, real numbers. Let's do one more example. Let's take this. Now, does the value of A change the domain?
No, ma'am.
It doesn't change the domain because for both for a greater than 1 and for both these cases, we know that the domain for this function log ax is the same, right? It's 0 to infinity. So domain is not affected by the base. That doesn't change anything. That's why I've taken simply x. And what's the domain of this function? If this is our function and the domain of f, for the domain of f, I just need to make sure that my argument, this entire thing under log function should be greater than 0, right? So I want square root of x square minus 1 to be greater than 0. That means I want x square minus 1 square root to be greater than 0 and less than infinity, which is obviously true. We don't need that condition. This will happen when, this is always true, by the way, square root is always greater than 0. The only problem is when whatever's inside becomes 0. We just have to avoid that part. Square root of every number is positive, right? Square root is a positive function. It renders only positive outputs. We are just worried about this being 0 because it anyway cannot be negative. This quantity can never be negative. We're only worried about it being 0. That means we just have to make sure that square root of x square minus 1 is not equals to 0, which is the same as saying x square minus 1 should not be equal to 0. Same as saying x should not be equal to 1 and minus 1. Do we have any doubts so far? That means the domain of your function should be equal to r minus 1 and 1. Is this fine?
Ma'am, also we have to exclude 0 as the root become negative at 0.
Yeah. Right. So that, okay, then let's do it that way, because to make sure that everything is included, that's why I prefer it doing that way. Let's consider this to be some other function. Let's consider this to be fog x, where my f will be log base ax and g will be square root of x square minus 1. Now the domain of this entire composition fog will be domain of g intersected with the set x such that gx is in domain of f. Domain of g is, let's come to that one later, domain of f is 0 to infinity, right? And domain of g is square root of x square minus 1. So the domain is basically when x square, yeah, we left this part, right? So it should be x such that x square minus 1 is greater than 0. This means x such that x square is greater than 1. And your x square is greater than 1, or maybe you can write this as, you want x square greater than 1. That's true when either your x is greater than 1 or your x is less than minus 1, right? Right?
Yes.
So that means there are a lot of ways to do this. One is to know that x square is greater than 1 when your x is greater than 1 or your x is less than minus 1. If you will take x from minus 1 to 1 in this set, your x square will be between minus 1 and 1 only, right? So if someone is not already, if someone thinks that you're not aware of this fact, then one thing you can do is just simply solve this equation. We've done this in previous class. You have to solve this, right? X square minus 1 is greater than 0. So you can write this as x minus 1, x plus 1, and then do it this way. Either you want both of them to be negative or you want both of them to be positive. And then solve it. This will give you x greater than 1, x greater than minus 1. No, less than, right? This will give you x less than 1 and x less than -1, and this will give you x greater than 1 and x greater than -1. So this will be, you can simply write this as x less than -1, and this you can write as x greater than 1. And because you want, so either this should be true or this should be true, right? So if I say that my x is either less than -1 or x is greater than 1, that means my x is either from -infinity to -1 or it is from 1 to infinity, right? So not just 0, you'll have to remove everything that's from 1 to -1, you'll have to remove everything. That means your domain of G becomes, either I write this as R minus the set -1 or the interval -1 to 1, or you can write this as -infinity to -1 union 1 to infinity. Is this okay?
Yes.
These sets are the same sets. They're the same. So and this one, you want Gx to be in domain of F. That means you want F. Yeah, you want Gx to be in the domain of F, and your Gx is this function, right? That means from this one, let me just call this set A because it's a very long set. I'm calling this set A. If this is set A, then my A set is Gx such that x such that Gx is in the domain of F, right? That means x such that Gx is square root of x square minus 1 is in domain of F. Domain of F is 0 to infinity. That means you want x square minus 1 to be between, you want to find x such that x square minus 1 square root is strictly greater than 0 and less than infinity, right? Now that means I only have a problem at, here you only have a problem at 1 because it's basically or you can, if you want to solve this entirely, you will have, let me solve this here. You have square root of x square minus 1 greater than 0. So this will be, don't take x to be plus minus 1, just remove these things. But if you remember, you've already removed them here, right? Ideally, you should be taking the same set here. You want this to be, if you want this quantity to be greater than 0, and I'm assuming that I'm taking it from the domain only. So that would mean that I should not be taking x, I should be taking from minus infinity to 1, minus 1 union 1 to infinity, right? Because between -1 and 1, this is not valid. You can't take a value, you can't take x to be between -1 and 1, and you can't take x to be -1 or 1 because this then will give you 0. And we can't take it to be 0, right? Is this okay? By the way, your domain, we have made a mistake here again. This should be greater than equals to. For your domain of G is square root of x square minus 1. So the domain of G should be x square minus 1 greater than equals to 0. You can also take this value to be 0. That's also fine, right? So this is included here. I'm making slight changes here. -1 and 1 are included here. You can include them. Because for Gx, we don't have a problem at x is equals to +1 and -1, right? They're valid for G, for domain of G. Then coming to domain of F, you want this quantity to be greater than 0. That means you want this to be greater than 0. This will give you x belonging to -infinity to -1 and 1 to infinity. So this set then is -infinity to -1 union 1 to infinity. And if I'll take the intersection of these two sets, what's the intersection of these two? This one and this one. Do you want me to show this on your real line, how these two look like? This is minus infinity on this side, infinity on this side. This is 1, 0, minus 1. So my domain of G was this. This not included. This is not included till this. This one. This entire thing. And this not included. This entire thing. Was this included? Okay, these two are also included. So this was my domain of G. Both of these were included. This was my domain of G. And for my domain for the other set, such that in that set, minus 1 and 1 and minus 1 were not included, right? In this set. In this set, minus 1 and 1 are not included. So it's this, and this, with this not included. Now, if I'll take the intersection where there is intersection means I have to find the set where we have red and green both. So red and green is so your red and green. If you will take the intersection of both these, you will get minus infinity to minus 1, union 1 to infinity, right? So that means your domain would become this. Minus infinity to minus 1, union 1 to infinity. Is this okay?
Yes, ma'am.
Does anyone have a doubt in this question, this particular one? This one. Then we'll move to the next one, if this one's fine. Okay, let's do a similar one. Log a 16 minus square root of x square minus 1. Now, instead of this, simply this, I've taken 16 minus this thing. Then what should be the domain? Domain is basically, you have to ensure two things. One is 16 minus square root of x square minus 1 is a valid function, right? So one is you have to take care of the domain of this function. And the second is you have to find x such that 16 minus square root of x square minus 1 is greater than 0, right? Or should I do it with the usual definition approach of D of FOG? Let's do it that way. Your fx will be, if this function is FOG, then your fx is log base ax. Your gx is 16 minus square root of x square minus 1. What's the domain of G? Domain of G you have to find, and then you have to intersect it with this set with x belonging to real numbers such that gx belongs to domain of f. Let's call this set A set. Domain of G is, your G is 16 minus square root of x square minus 1. So this is not a problem, only this part is a problem, right? If you have to find the domain of this, 16 minus is not causing any problem. Only this thing is going to cause a problem. So for this, you just need to make sure that x should be such that x square minus 1 is greater than 0, right? Greater than equals to 0. And this, we've already done this in the previous question. This came out to be minus infinity to minus 1, union 1 to infinity. So the domain of 16 minus square root of x square minus 1 and square root of x square minus 1 is same. They have the same domain. Then the next part is A, where you have to find the values x such that gx is in domain of f. Let's first find what domain of f is. Domain of f is the logarithmic function, so its domain is 0 to infinity. So that means you want x belonging to real numbers such that gx is in domain of f. That means gx is in 0 to infinity interval. And what is gx? Gx is this, right? 16 minus square root of x square minus 1. That means you want x such that 16 minus square root of x square minus 1 belongs to this interval. Right? Let's find such x. I want 16 minus square root of x square minus 1 to be greater than 0, strictly greater than 0. And this is obviously less than infinity. You don't need this condition anyway. You can drop this one because this is less than infinity, right? This number is between infinity and minus infinity. These conditions are not needed. You can leave this one. So you have to find x such that x belonging to real numbers such that this value is greater than 0, strictly greater than 0. X for which this value is greater than 0. This is the same as saying x such that square root of x x square minus 1 is greater than 16, right? And this is the same as saying x such that, now if I'm saying square root of some number should be greater than, let's say 2, then that means that we have two conditions here. One is that this should be valid. So for this, I'd want x to be greater than 0. And then the second one would be squaring on both sides, right? Square root of x function is this. For positive x, when you have made sure that x is positive, then your square root function is this. And this is a 1, 1 function. Now, if this is a 1, 1 function, that means okay, let's say if I have a, if I say fx is a 1, 1 function, and I say x1 is equals to x2, then I can say that fx1 is also equals to fx2, right? So we're doing the same thing here. If I say, can I say x square is 1, 1 from 0 to infinity?
Yes, ma'am.
Right? So that means I can square these both of these sides, right? Because both of these numbers are positive. Now, if I have x1 less than equals to x2, or your x square is increasing too. In fact, it's strictly increasing, right? Strictly increasing on 0 to infinity. X square is strictly increasing, or your x square looks like this. That means it's strictly increasing. Now, if I have 2 here, square root of x here, and this is the inequality between these two, then the square of 2 and square root of root x should hold the same inequality, right? Because it's an increasing function, strictly increasing function. That means and 2 and square root of x belong to 0 to infinity. That means if 2 is less than equals to square root of x, then 4 should be less than equals to x, right? But this was the case when I had x here. You need to know this, that this only holds, this thing only holds, the squaring part only holds when you have different numbers, when both of these are on the positive side. Because both the numbers were here, that's why the square of both the numbers will follow the same inequality. If x1 is here, x2 is here, then x1 square will be less than x2 square only when they're both on the positive side. That means only when both of them are greater than 0. That's what we're doing here, because 2 and square root of x both are positive. That's why we can do it. If we had minus 2 and square root of x, then maybe we cannot do this thing. If I have a negative number here and a positive number here, and I'm saying that this number is less than this number, I can't say that the square of this is also less than the square of this, right? That's what I'm trying to tell. We can use this thing because they're both positive. Okay. So this is the condition that you get when you have 2 less than square root of x, right? But we initially had this thing. This is rough. We want this square root to be greater than 16. That means, what is 16 squared? 256, right? That means I want x square minus 1 to be greater than 256. We did this here, but we have squared both of these sides because we know that both these numbers are positive. That's why we can square both the sides and the inequality is not going to change. Now this is the same as x such that x is greater than 255, right? Strictly greater than 255. X square is strictly greater than 255. That means x is greater than square root of 255 and less than square root of 255 with a negative sign. Or if you don't want to do it this way, you can do it this way. Add one more step, you will have x square minus 255 greater than 0, strictly greater than 0. This will be the same as saying x minus 255 and x plus 255, square root of 255 greater than 0, right? That means I want both of them to be negative or both of them to be positive, which is going to give you, we have done the same thing earlier when we took x square minus 1, we did the same thing there, right?
Ma'am, I think you made a mistake,
Where
as under root x square minus 1 should be less than 16, not greater than.
this one,
Yes, ma'am.
yeah. We had a negative. Okay, if we'll take it on that side, they're both negative. Okay. So we'll have to change this thing here then. It remains the same thing because both of these numbers are positive. That's why if this is less than this, then the square of this is going, if this is greater than this, then the square of this is going to be greater than this because they're both positive. That's why. So only this is going to change. And then here you will have x square 256 minus 1. So you will change this to. And now I want x square to be less than, now things change, right? If you want, that means you want this thing.
And ma'am, 255, instead of 255, you have 257, as the minus 1 will get added up.
Okay. We have 257 here. Fifty-seven, 57, and 57. That means if you want this quantity to be less than 0, this time we want this to be less than 0. That means you want this to be negative, this to be positive, or this to be positive, this to be negative. Let's do this one. That means x, for this case, you'll have x minus 257 less than 0. That means x less than square root of 257, right? And x, from this one, you want this to be greater than 0. So this will give you x greater than minus square root of 257. So if this is 0, your 257 is here, square root of 257 here, minus 257 square root here. You want x to be less than 0, x to be less than this thing. That means here. and x to be greater than this thing, that means here. That means you want x to be between these two, right? So this implies your x is between minus 257 square root, this one, and this one, right? If anyone has a doubt, if we're going too fast, you can unmute yourself and ask. And this one will be x greater than square root of 257 and x less than minus square root of 257. Now this is not possible because if you have minus square root of 257 here, 0 here, plus square root of 257 here, then you want your x to be, less than this and x to be greater than this simultaneously. That means you want both these conditions to be true together, which cannot happen, right? That's why this set means not possible. This is not possible. So what should be this set? The set that we were looking for is this set that we've called A. So A should be equal to this one, right? Your A set is this. Minus square root of 257 and square root of 257. Right? This set that we were looking for here, we found it here. This is your set. Then the other set, which is, we've already found this one. We have also found this one. We just have to take the intersection of these two. So the intersection will be, you have to take the intersection of these two sets. DG is minus infinity to 1, union 1 minus 1, 1 to infinity. And the other one, the A set, was minus square root of 257 and square root of 257. So this is something like 16 point something. So this will be minus 16 point something to 16 point something, that same 16 point something, right? You have to take the intersection with this one. So this is minus infinity, this is plus infinity, this is minus infinity to minus 1. Let's say this is minus 1. So this is your set. And this is 1. This is the same set. Just 1 second. This set is this one. The red marked one is this one. And then let's take this one. And the green marked one is this one. So the green one is minus 16. Minus 16 will be somewhat here, right? Minus 16, not included though. This will be minus 16 to plus 16. Plus 16 is here. This is it. So what's the intersection of the red one and the green one? It's minus 16 to minus 1, union 1 to 16, right? Is this okay? Does anyone have a doubt so far?
No, ma'am.
No, ma'am.
Okay. Shall we do more questions on the domain of log functions? Let's do one more. Let's do this one. Then the domain of this should be, for the domain of this, you would want minus e to the power x minus e to the power minus x to be greater than 0, right? For the domain part, you want this to be greater than 0 and whatever this function is. And if you want a shortcut here, if you have anything, because we've been doing the GOF domain thing, each time we are finding the domain of log functions, we're using this definition. If you want to avoid this definition, you only have to make sure of two things. If you have log of fx, one is you have to make sure that f is well defined. So you have to take the domain of f and you have to intersect it with wherever this function x fx is greater than 0. That's it. This will be the domain of, if I say this function is g, then the domain of g is going to be this. Domain of f intersected with x such that fx is greater than 0. So the domain of this thing is domain of this entire thing. What's the domain of this function? Minus e to the power x minus e to the power minus x.
All real numbers.
Right. So the domain of this is all real numbers, because you can choose the input to be anything, right? No number is a problem. And then you have to make sure that minus e to the power x, this thing, is greater than 0. So this is minus 1 by e to the power x minus e to the power x greater than 0. This is 1 plus e to the power 2x by e to the power x greater than 0. We have a negative sign here. This is equivalent to saying, so if I say minus a is greater than 0, that means my a is less than 0, right? We're using the same thing here. If this is greater than 0, then 1 plus e to the power 2x by e to the power x should be less than 0. Now you want this to be less than 0, right? That would mean you want either both of these. This is the numerator, this one, this and this. Let's call either you want the numerator and denominator both to be positive. If I have this f by g and I want f by g to be greater than 0, that means either f and g both are greater than 0 or f and g both are less than 0, right? Positive, positive, that will give me a positive sign, or both negative. So it will give me again a positive sign, right? So if I want this to be happen, that means I want this to be, because this is less than 0. Now if I say m by n is less than 0, that means m is either m is greater than 0, n is less than 0, or m is less than 0, n is greater than 0. That is either this is positive, this is negative, or this is negative, this is positive. So this would mean either 1 plus e to the power 2x by e to the power, either both of these ones, numerator, denominator, both have opposite signs. So either this is greater than 0, e to the power x is less than 0, or 1 plus e to the power 2x is less than 0 and e to the power x is greater than 0. So let's take this first case, this second case. If I'll take first one, e to the power 2x greater than minus 1, this one, and e to the power x less than 0. What does this mean? If I'll take this, I can write as e to the power x and square, right? And e to the power 2x, you don't have to find this thing because this is always true, right? E to the power 2x is always greater than minus 1. In fact, e to the power 2x is always greater than 0, right? This one is always true. And this one, if you notice, is never true, because e to the power x function is never negative. That means this case is not possible. Because you wanted both of them to be, you wanted to find x such that e to the power 2x is greater than -1 and e to the power x is less than 0. But this second condition is never true. That's why this case is never possible. Then the second case said e to the power 2x less than -1. Now this is also never true. E to the power x greater than 0. In this specific case, this is never true. This implies this case is also not possible. If you don't want to go into such long analysis, you can directly see from here that I wanted this thing to be positive, right? I wanted the interior of this function, natural log function. We've already discussed this, that when we're discussing log functions, whatever is in here should be positive, strictly positive, right? It shouldn't even be 0. And we this time have e to the power x plus e to the power minus x with a negative sign. And this thing is always greater than 0. So minus of this thing will always be less than 0. That means this entire argument of log can never be greater than 0, no matter what x I take. That means this does not even have a domain. This function is not valid. Is this okay? What's the domain of this then? Let's do one more example, which is, let's say instead this time I have log of base x minus 1 x plus 1. And here I have x square minus 4. Let's say this is my function. This time my base is also varying. Notice that my base is not a constant here. It's not a fixed number here. That is also variable. What should be the domain of this function? So for domain, you need to make sure of these things. First is x square minus 4 is strictly greater than 0 because the argument of log function is always greater than 0. First is this thing. Second thing is x square minus 4, you have to take care of domain of x square minus 4, right? Third is, but this is because this is real numbers only, that's why this is not important. Third, that's important is your base. We've already discussed this thing that if you have log base ax, then a should be greater than 0, right? And a should not be equal to 1. So you have to make sure that x minus 1 by x plus 1 is greater than 0, and x minus 1, x plus 1 should not be equal to 0. Which gives you just have to solve x, you just have to find x such that it satisfies all these three conditions, right? So the first condition will give you x square minus 4 greater than 0. That means x square greater than 4. So it will give you x belonging to minus infinity to minus 2.
Ma'am,
Yeah.
in the third condition, it should be x minus 1 upon x plus 1 should not equals to 1, not 0.
Yeah. Yeah, that's all. Yeah, this is 1. The not equals to 0 case is already included here. Okay. So this is it. So first condition on x is that x should be in this interval, minus infinity to minus 2 and 2 to infinity. Then this one is, there is no condition from here, right? You can take x to be any real number. So no condition from here as such. And then from this one, you will have x minus 1. X minus 1 by x plus 1 not equals to 1 means this should not be equal to x plus 1. And x minus 1 is anyway never equal to x plus 1. So that means you don't have to check this condition. This condition is never true for any x, so don't worry. X minus 1 by x plus 1 is never 1. This is not causing any issue, then let's come to this one. X minus 1 by x plus 1 should be greater than 0. That means I want either both of them to be greater than 0, x minus 1 and x plus 1, or I want both of them to be less than 0. So this will give me two things. One is x minus 1 greater than 0 and x plus 1 greater than 0, or both of them less than 0. So this case gives me x greater than 1 and x greater than minus 1, which is simply x greater than 1. And this case gives me x minus 1, x less than 1 and x less than minus 1, which is simply x less than minus 1. So either x should be greater than 1 or x should be less than minus 1. So this will give me x belonging to minus infinity to minus 1, union 1 to infinity. So this is the second condition on x, that x should be in this interval, union of intervals. And the first condition was this, that x should be in this one. Now, if I want to make sure that x is in both, that means x is in minus infinity to minus 2, union 2 to infinity, and x is in minus infinity to minus 1, union 1 to infinity, then that should mean that your x is if this is minus 2, this is minus 1, 0, 1, and 2, then this interval, this one, is this. And this one is this. So the intersection of all of these would be this. Minus infinity to minus 2, union 2 to infinity. Is this okay? This is where you
Yes,
have
ma'am.
red and green both. So this will be your domain, required domain. Okay, then we'll move to the other thing. One point that I wanted you to note is because your log is an increasing function. That's why whenever you see something like this, let's say you have been given log ax less than log ay, then this should mean that your x is less than y when a is greater than 1, and when a is between 0 and 1, your x should be less than y. Sorry, greater than y. Which is because for a greater than 1, your log is an increasing function, right? So if x is less than y, log of x will be less than log of y. And for a between 0 and 1, your log is a decreasing function. So if x is greater than y, log of ax will be less than log of ay. Is that okay? This is one thing that you should know. Then let's do some other kind of questions that you might find in Portal. Let's solve this one. Let's say you have a question of this form. Then to solve these kind of questions, all you have to do is either you can take natural log on both sides. So if you take natural log here, you will have natural log of 4, 2x plus 1. And here you will have natural log 2, 2x square plus 7x. So this will give you 2x plus 1, natural log of 4, natural log of 2, and this will come out. So this will be 2x square plus 7x, right? And natural log of 4 can be written as natural log of 2 square. So I can write this as 2 square, and then this 2 will come out. So this will be 2 here, natural log of 2. These 2 will get cancelled. So 2x plus 1 is equals to 2x square plus 7x. And then you just have, this is a quadratic equation. Solve this and you can find the solution to this equation. And with this, I'll also write log is a 1, 1 function. Both log ax, this function, if I call this fx, and if I call gx is equals to a to the power x, both are 1, 1. They're both 1, 1 functions. So if you ever see something like this, log ax is equals to log ax square plus 1 or something like this, you can just remove the log from here, right? Because they're 1, 1 functions. That means if log of x and log of x square plus 1 is same, that means x and x square plus 1 are also same. That's what 1, 1 means, right? Okay. Then let's do one more example. It's this one, 2 to the power x plus 1, 5 times 2x plus 3. Now let's say some equation of this form is given to you. Then you have to identify these things. This is 2 to the power x here, and you see something of the form 2 to the power x here as well, which you can write as this. You can write as 2 times 2 to the power 2x, right? This thing. And this is the same as 2 to the power x whole square plus 5 times 2 to the power x plus 3 is equals to 0. Now, if you'll observe this very carefully, you will see that this is of the form 2 t square plus 5 t. I'm replacing 2 to the power x with a t plus 3 is equals to 0. And you get a quadratic equation here. So now instead of solving this thing, you can simply solve this equation. What will be the roots from here? So you'll have 2t square. By factorization method, you can have this. This will be 3t plus 1, and here you'll have 2t, t plus 1. This will be t is equals to minus 1, and t is equals to minus 3 by 2, right? So these two will be the solution. That means if your t is equals to minus 1, two minus 5, right? So if your t, the two solutions for this equation are t is equals to minus 1 and t is equals to minus 3 by 2. Now, if my t is equals to minus 1, that means 2 to the power x, because I've taken 2 to the power x to be t, right? That means 2 to the power x is minus 1. And for this one, you will have 2 to the power x is equals to minus 3 by 2. From here, you have to find the values of x. But we already know that for no value of x, 2 to the power x is minus 1. We've discussed this, right? A to the power x is never negative. Provided you have a positive, if a is greater than 0, a to the power x is also greater than 0. That means this is never possible. And this is also never possible. Instead, let's say you had, if instead of this one, if we had this thing here, if we had a negative sign here, then you will have one solution will be 1. And the other one will be 3 by 2, right? Then the value of t that will satisfy this equation will be t is equals to 1 and t is equals to 3 by 2. Now then you have to equate 2 to the power x is equals to 1. This will give you x is equals to 0. And then you have to solve this one. 2 to the power x is equals to minus 3 by 2. This will give you x is equals to plus 3 by 2, right? This will give you log base 2 3 by 2. If you have something, we have done this in properties, right? That if you have 2 to the power x is equals to 3 by 2, then log base 2, if you apply log base 2 on both sides, you will get this is x only. Log a to the power x is 1, right? We've discussed this in properties. So you can apply log base 2 on both sides of this, you'll get this thing. This will mean that x is equals to this log base 2 3 by 2. You don't have to find the value. That means your two solutions are x is equals to 0. This is one solution. And the other solution is x is equals to log base 2 3 by 2. Is this okay?
Yes, ma'am.
Okay, then let's come to let's do one more example. Let's do this one this time. So how do we solve this thing? We have to find, obviously, we have to find the value of x such that this equation is true for that x, right? So we already know that log a to the power n x is the same as log a x to the power 1 by n, right? So we'll use this property. We've discussed this properties when we were discussing the properties, we discussed this one, right? And the other property is this simple one, where we said that log of a x plus log of ay is the same as log of a xy. These are the two properties that are used in this question. This will become log 2x plus 1 minus log, this is 2 square, right? 2 square x minus 3 is equals to 2. So this will give you log base 2 x plus 1 minus log 2 and square root of x minus 3, right? Is equals to 2. Why we're doing this is because we want the basis, we want log of something is equals to a constant here. If we have something like that, if we have log of this thing equals to this, instead of having log plus log again plus log again, we want one log so that we can take this log on the other side. We can have this thing equals to a to the power k, right? So that's why we're clubbing all of these together. So if I club these two together using this property, and in this one, we're using the negative one, right? Negative. So this will be x by y. Log base 2 x plus 1 by square root of x minus 3 is equals to 2. This means x plus 1 by square root of x minus 3. Now take log on that side, it will become 2 to the power 2, right? If I have log a, x is equals to t square, let's say, or let's say just t. Then if I take log on the other side, I get x is equals to a to the power t, right? That's how things change. So same thing we're doing here. Which is equals to 4. And then this one will become x plus 1 is equals to 4 square root of x minus 3. Then you will need to square both sides to find the solution. This will be x square plus 2x plus 1. Other side will be 16 x minus 3. So this gives you x square 2x minus 16x. So this will be minus 14x. 1, 16 minus 3, 48
Plus 49. Plus
plus
49.
49 is equals to 0. And
X
this is a
minus 7
quadratic
whole square.
equation.
Yes, ma'am. X minus
Okay.
7 whole square.
X is equals to 7.
So your solution will be x is equals to 7. Is this fine? So that's how you solve the questions based on log. And if you've been given log a lot of times, like let's say you have log, some questions are like this as well, where you will have log. Okay, we'll do these questions when we'll do solve with us. We'll see what kind of questions are there. Let's do other things for now. Let's just come to, we've already discussed the graph of a to the power x and log base ax, right? These two are inverses of each other. And we have seen that they are symmetric about the y is equals to x line, right? For a greater than 1, we add this thing. And this, I mean, they don't look very symmetric, but they are, right? And for a between 1 and 0, we add this thing. This is a very rough diagram, rough graph. This is y is equals to x line, and this was your graph, log graph. This is a to the power x, and this is log ax. And then one more thing, which is not particularly related to this week, but I wanted to discuss this thing as well, is when you have fx, let's say your graph of fx is given, then you can also figure out what's the graph of f of minus x, minus of fx, and f of x minus 1, and fx minus 1. Let's say we have to find the graph of these. Given the graph of fx, you have to find these graphs. Let's say, so let's take a parabola only for now. Let's take a parabola which passes through the point 0, 0. So if it passes through 0, 0, then f of minus x becomes, if this is y is equals to fx, then y is equals to f of minus x is reflection about y-axis. So what happens there is, if you have y is equals to fx, let's say this is f of 1, this is 1, and this is f of 1, then this should be here, right? This is not going to change anything because it's already symmetric about this line. Let's take some other graph. Let's take e to the power x graph, for example. It looks like this. Then if I'll take f of minus x, this will be reflection of fx about y-axis. So if you're taking a negative sign in front of x, it will be a reflection about y-axis. So if this was fx function, then your f of minus x function will be this. The reflection of this function about y is equal to y-axis, or x is equals to 0 line. This will be f of minus x. And similarly, let's say you have If this is your f of x, then y is equals to minus fx will be this one. This reflected about x-axis. So it will be this. This will be minus of fx. Similarly, if you want to take, let's say this is the point 0, 1, right? In e to the power x, this point is 0, 1. And let's say I'm taking, instead of e to the power x, this time I'm taking e to the power x minus 1. So for you to plot this one, you will need, so you have y is equals to e to the power x minus 1 this time. That means this gets shifted 1 unit up here. So this e to the power x minus 1 graph will be here. This same graph e to the power x gets shifted 1 unit up here. Or not here, actually on this side. Basically, when you have y is equals to fx, if you do y is equals to fx minus a, then your graph gets shifted a units towards the right here. That means if you have this graph, then this will get shifted a units towards here. So if you have this one, y is equals to e to the power x minus 1, this needs to get shifted here. 0, 2, and it will pass through this one then. Same graph, but it has just shifted here. I have not drawn this very properly, but the entire thing gets shifted here. Is this okay? And similarly, the same thing happens when you have y is equals to ex plus 1. So this means you have y minus 1 is equals to e to the power x. So the graph for this one looks like this. E to the power x graph is this. And for y minus 1, this gets shifted here. So you have 0, 1 here. This time you'll have, this is wrong. This is 1, 1. This will be 0, 2, and this is it. Is this okay?
Yes, ma'am.
So this is how you shift origins. If you have been given a particular graph, let's say you've been given e to the power 2x minus 1, then you should know how to plot such graphs, right? Let's say this one. So if you know how to plot e to the power x, you can also plot this one. Or if you have plus 1 here, you can plot all of these graphs. This is all this is about. That's it. So I think we're done with the summary for this week. If anyone has any doubt in any particular topic, you can ask. Otherwise, we can end this session here.
Hello, ma'am. I have a doubt in graph.
Which graph?
No, ma'am. Like we know the graph of e to the power x.
Right.
So how the graph of e to the power 2x look like, and how the graph of 1 by 2 e to the power x look like? Yes, ma'am. And e to the power 2x.
Let's start with this one first and let's come to this first, right? This means if you have, this one looks like, this is e to the power x. So this is like this, right? Where this point is 0, 1, right? Now, if I'll have this thing, this thing is going to remain same. This still intersects y-axis at 0, 1. Things that are going to change is, see, if I put x is equals to 1 here, I'll have e to the power 1. But if I'll put x is equals to 1 here, I'll get e to the power 1 by 2. That means I get a smaller number, right? That means here my height is increasing more than it is increasing on this side. When I have e to the power at 1, I have e to the power 1, but at 1 here, I have e to the power 2, e by 2, right? Similarly, for 2, I'll have e square, but here I'll have e square by 2. That means I get smaller numbers here. For the same x, I get smaller y's, which would mean that if I have this graph, it still crosses through this one, but my height, it will be less than this. Similarly, if I'll take something negative, so the graph will change like this. So if this is e to the power x, then your e to the power x by 2 will be something like this. Is this okay?
Okay, ma'am. And now e to the power 2x.
Wait, I didn't check very properly for the negative side. The positive side is surely in this manner. I'll have to check for if the positive side is down, no, it has to go up from here, I guess. Yeah. But for confirmation, let's take negative values too. Yeah, it's the same thing. And for e to the power x, this one, right?
Yes, ma'am.
So this one will be, if this is, let's say, if this is your e to the power x curve, let's do this one here. In comparison to e to the power x, if this is e to the, if this is e to the power x, then let's do for e to the power x, e to the power 2x, right? When I put y is equals to 1, I have x, when I put x equals to 1, I have y equals to e. At x equals to 2, I have y equals to e square. Let's do these things here then. At x equals to 1, I have e square. At x equals to 2, I have e to the power 4. Now this means for the same values of x, I get higher value of y, right? My y is more than this y. That means my height is increasing for the same value of x. So it should be here, right? This point will remain same. They both intersect, this one and this one both intersect the y-axis at the same point 0, 1. But the change will be here. Why is it so? Because at x is equals to 1, I see here I have e for this graph, and here I have e square. E square is greater than e. That means at this point, the value of this function, the height of this function is greater than this function, right?
Yes, ma'am.
And if I'll do it for -1 as well, I'll have 1 by e. Here I'll have 1 by e square. But on here, I'll have 1 by e square and 1 by e to the power 4, which means, now which one's lesser? This one or this
1
one?
upon e to the square. 1
This
upon e
one's
to the
lesser
square.
and this one's lesser, right? That means this graph on the positive side, on this side, when x is positive, e to the power 2x is greater than e to the power x. And when x is negative, your e to the power 2x is less than e to the power x, right? So it'll be like this. Is that okay?
Yes, ma'am. In the previous case, y is equals to half e to the power x. It should pass from 0, half, not 0, 1.
Yeah, okay. That's also true. Just 1 second. This is y is equals to, if I'll put x equals to 0, I'll have half, right? So it'll be half comma 0, which 0 comma half, which is here 0 comma half Then we'll need e square. Here we'll have e by 2, e square by 2. And for e to the power, let's say 0.1, we'll have e to the power 0.1 by 2. Yeah, so that means this function is always less than this one, right? So it should be this. This stays below this, and on the, I'm not sure about the negative one too. Let me just check for the negative one. This will be e to the power minus 1. At minus 1, you will have e to the power minus 1, e to the power minus 1 by 2. E to the power minus 2, e to the power minus 2 by 2. That means this is still okay. This is still less, right? It remains permanently less than this. This is e to the power x by 2. Is that okay?
Okay, ma'am.
Okay. Anything else? Can we end this session here then? Okay, so I'm
Yes, ma'am.
okay. So I'll stop the session here.
Okay.